Okay, we have been discussing about prediction of ship resistance from model test. There are different methods for predicting the resistance from model test. One of the method is put forward by Telfors and known after him as Telfors prediction method. You can see here the graph shows total resistance coefficient, usually it is put as 10 cube Ct because the value of numerical value of Ct is quite small. So, it is better to plot 10 cube Ct and against the Reynolds number here. So, here in the Telfors method he tries to satisfy a Reynolds number and Froude number from the model test. So, here what he does is, maybe if you see the next slide, it gives more better explanation for that. Telfors tried to combine, as I said, Froude and Reynolds resistance similarity. That is a specific total resistance. You can see that R by rho s v square, which is representing a Ct, is going to be a function of Froude number and Reynolds number. So, what it does is find out the specific total resistance Ct from geometrically similar vessels at different scale ratios. So, he uses models of different sizes, that is different scale, and you find out Ct from that, and then you try to extrapolate it to the prototype. So, here he keeps, that is by keeping the constant Froude number over a range of Reynolds number. You can see that here in the graph, what he considers is, he considers this is the scale of the model 50, 36, 25, 21, 18, 15 and goes to finally to the ship, that is 1. So, this ship is 1:1 scale. So, when it moves to this side, the size of the model is coming down, or you say this is the smallest model, then the size of the model increases. So, it does up to 15, then you extrapolate the trend to that of the ship 1:1. So, here what you have is, you are considering the finding out the resistance for that model, where you keep Reynolds number constant means for the length constant Reynolds number, and then you find out what is the total resistance and resistance coefficient. So, then you plot it here along this axis. Now, since I said it is a length constant Reynolds number, you know the Reynolds number is equal to VL by nu, and where you put L is equal to constant, because for the same model, the V changes during the small range in the velocity, that is V of the model goes by the change as per the Froude assumption, that is the Vm is equal to Vs by square root of lambda. So, that is the variation what you see here in this axis. So, that is what it is called. So, here you get the resistance for that model at different speeds or different Froude number. Actually, for different Froude number you have, each point is a Froude number. So, for a particular Froude number you have resistance and you just plotted it here. Now, you go to the next model, which is a bigger one, the scale is 36. So, for you run the same, you make the model, run the model in the towing tank, then you find out what is the at each Froude number, what is the total resistance and resistance coefficient, plot it here. Similarly, you do it for the different Froude number and you get this curve. So, you repeat that for a bigger model scale 25. So, you have Froude number varying like this and you get the total resistance coefficient. Then you do for the next bigger model 21 scale, you got this curve. You go for the bigger one, you got this curve, and higher one. So, you got a set of curves from one curve from each model, so which represents the total resistance coefficient. So, now what do you do is you connect the points of the same Froude number. Here you can see the Froude number is 0.26, this line representing 0.26, fruit number 0.25, 0.23, 0.22 like that. So, each line representing each fruit number. So, how you uptake what is? So, you have the fruit number here, that is 0.28, next curve you get 0.28, next curve you take another point, you join all these points, you get this line up to 15. So, you have tested model up to a scale of 15, that is the biggest model you have tested, 15, scale factor is equal to 15. Now, you connect this point, next fruit number of 0.25, you can see this 0.25. So, you have connected a similar fruit number points, you have taken up to this point. So, you have done the same thing for other fruit numbers. So, you get these curves up to 15, okay. And now what you do is you extrapolate this curve to this value, to scale of 1:1, extrapolate this curve with these curves to the ship, that is 15 scale to scale of 1, that is the ship. So, that is how the Telfer prediction method, Telfer uses the prediction method where he tries to satisfy the Reynolds number and also the fruit number. And here you can see that this line, which is given by the frictional resistance line, which we have already discussed, it is a Schoner formula in frictional resistance, which we discussed in one of the previous classes. So, this is a line representing that. So, it has been observed that these constant fruit number lines are following almost parallel same trend as this line. So, he has used this as a reference line for the extrapolation of these lines to 1 scale. So, this is based on observation, this line has been observed to following or parallel to this up to this range, and we have the information for this line up to here. So, we just use this as a lines parallel to that. So, that is how he got the resistance of the ship. So, here that is how he tried to combine both Fruits and Reynolds laws, and we know that resistance coefficient is given by fruit number and Reynolds number, he is trying to satisfy both. So, here if I enter the specific total CT for geometrically similar vessels, it is not one vessel, he has tried many different small model, bigger model and much bigger one of different scale ratio. By keeping constant fruit number, we have seen that it is a constant over a range of Reynolds number. So, we considered for the whole range of Reynolds number, he has a fruit number curve for 0.26, he has a fruit number curve for 0.25 like that. So, that is how what it explains here. Similarly, at constant length Reynolds number, the variation could be studied for a range of speed length ratio, since the Reynolds number is constant and Cf is constant. So, here that is what is done. So, here it is assumed to be a constant length Reynolds number, L is kept constant because of the same model. So, this is studied for different fruit number, he has this one, and for different Reynolds number depending on that you have this. So, it is trying to satisfy both in the same test. Thus, only change in CT and only change in the resistance coefficient, total resistance coefficient with fruit number would be due to wave making. So, what do you consider is only change in CT with fruit number. If you consider along the same Reynolds number and with fruit number, only change is due to wave making. All contours of constant fruit number are mutually parallel, that is what you have seen, all the constant lines are, say all these lines are parallel, that what is mentioned here, mutually parallel. CT contours of constant length Reynolds number against fruit number base are also parallel to each other, that is these curves are also parallel, these curves are also parallel to each other. So, that is that was CT contours of the constant length Reynolds number against fruit number base are also parallel to each other, that is a vertical slanted line in the figure, that is what you have seen. Extrapolate the model values to that of the ship range, that is what I said, you extrapolated that, then you what it is, that is a model resistance, then you give roughness allowance and air resistance allowance need to be added to ship CT. So, which is not present in the model test. So, the roughness allowance, because the ship model surface is very smooth and the ship surface is not so smooth. So, the roughness is different and you have to give extra allowance to account for the variation in the roughness between the model surface and ship surface. Air resistance is not measured, so give allowance for the air resistance also. So, from which you get the total CT of the ship. So, say from the CT of the model you put these two allowances to get the CT of the ship and obtain from the extrapolation. The CT curves for constant Froude number is nearly parallel to the Schoner formula. That is what I have shown before. You can see here these curves are almost parallel to this curve. This is a Schoner formula, flat plate resistance formula put forward by Schoner. So, you have this formula here. So, this is actually I think CF, it is not CP. So, here you have that. So, this line can therefore be used to reference line for the parallel extrapolation. So, this line is used, the Schoner line is used for the parallel extrapolation, because see you can, if you consider you have points only up to this point, now you are extrapolating a long way to the ship. So, even a small change in the trend makes lot of difference when it reaches here. So, you do not want that to happen to minimize error, and it has been found that parallel to this, which gives a trend, is more reliable, and hence the lines are, these lines are made parallel to the Schoner line. So, that is why this line can therefore be used as a reference line for the parallel extrapolation. The ship resistance, now you have got CTS, from which multiplying it by half rho ship vector surface area, ship velocity square, that gives the total resistance of the ship. So, that is how the ship resistance is predicted from a model test by Telfus, and he tries to satisfy the Reynolds number and Froude number in the model test. But there are a lot of disadvantages or problems with Telfus method. The Reynolds number distance from model to ship is very large. We have seen that the Reynolds number which you consider from model is Reynolds number here, whereas the ship is Reynolds number here. So, this is a long variation, the gap is so high, so extrapolation may lead to problems. So, this is very large, hence even a minor inaccuracy on the extrapolation can lead to large error on the forecast. So, any prediction of the ship resistance from the model test and which got extrapolated over such a gap can lead to inaccuracy, major problem there. For big models, kinematic dissimilarity around the ship model due to tank wall. So, if you are using, he has used models for 52, say 52, 15, when it comes to a scale of 15, the model size is so big, the big models, that is mainly the breadth of the model, and it may create a tank wall effect. The tank is not wide enough, this may create tank wall effect, and that lead to inaccurate predictions. So, hence that is what it says. You can see for big models, kinematic dissimilarity around a ship model due to towing tank wall interference. So, towing tank wall interferes and resistance recorded will be wrong. Wall effects also leads to increase in resistance, that is what is a wall effect, again leads to increase in resistance. When testing small models, so the lowest model is scale of 50, that is a very small model. So, flow over such small models become laminar, the Reynolds number is very low and the flow become laminar, which again deviates a lot from the actual flow around the ship, and hence the kinematical similarity is totally apart. So, hence the measured resistance is less than the actual when turbulent flow is to be encountered in a higher ship. So, when you consider the turbulent region and the laminar region, we know that resistance coefficient is higher, frictional resistance coefficient is higher at low Reynolds number or at laminar region, and frictional resistance coefficient decreases when it goes to the turbulent region or in the high Reynolds region number region. Testing with a family of models. Now what you have to do is, you have seen that we are using many models. We have to have models with the different scales, one model with 50 scale, another model with 36 scale, another model with 25 scale. So you need so many models of different sizes if you want to use the Telfors method. So model making is expensive and time consuming. So you can see that testing with a family of models for a range of lambda required, it is expensive and it is also time consuming. So these are the disadvantages, problems with the method. So considering all these aspects, disadvantages and all that, and cost involvement, facility limitation, many of these aspects, the method put forward by Telfors is generally not acceptable, or practically it is not feasible. So it is not picked up. So we see what are other methods available. Next method is Hughes method for the prediction of ship resistance from model test. So based on the experiments on frictional resistance of smooth plane surface in turbulent flow, Hughes proposed. So he has considered plane surface in turbulent flow, experiments on the frictional resistance of smooth plane surface, CF. So what he has done is, this also again based on plate surface, and he has come out with the plate frictional resistance based on the experiment. CF is equal to approximately 0.067 divided by log 10 Rn minus 2 the whole square. This is the expression put forward by Hughes based on his studies. So Hughes, what he put here is, the total resistance is now constituted by the base frictional resistance at the flat plate, which you have seen using the previous formula, plus the form resistance deeply submerged double hull model. So double hull model is the one which I discussed before. So it is a formed resistance plus free surface resistance, that is the wave making resistance. So this is a basic frictional resistance into R, that is a flat plate resistance into R. R takes care of the formed resistance plus the free surface resistance, where R is a resistance ratio and is a constant factor for a given hull form. So you find out what is R, and that use that R is equal to 1 plus K, K is called the form factor. We will see in the next figure, next slide, what is how this is estimated, 1 plus K and all that. Yeah, what is that is done here. What it does is, you have 10 cube CT against Reynolds number, and you use the same formula, what the Hughes formula. You can see that this is the Hughes formula. So this, with that you plot the baseline. The baseline here you can see, that is based on this expression, which is depending on Reynolds number. So you have the Reynolds number here, and you use this plot is obtained from that formula. Now you do the model test, you find out the total resistance coefficient for the model. This is the model region. So for different fluid number, different fluid, that is for different fluid number, you get the resistance coefficient here. So you plot that, then you join it with a curve. So it goes like this, basically something like this. So this is a resistance curve. So what you do is, now you draw lines, this baseline into 1.1, you get this line, into baseline into 1.2, you get another line, baseline into 1.3, you get another. So you keep doing up to, I think, up to 1.5. So you get so many lines, which is obtained by multiplying this formula into these factors. So you get lines which come like that. So now at this lower region, you find that the resistance curve, the model resistance curve, it usually goes like this, it comes like this and it goes like that. So this is at the very low fluid number. At very low fluid number, the wave making effect is less. So the major effect, or the whole effect, is coming from viscous one. So there is no wave making at very low fluid number. So, at very low fluid number, if you do the test for few speeds at very low fluid number, then you get the resistance exclusively by the viscous effect. So, if you find that this trend of the curve, if it is coinciding between 1.2 and 1.3 somewhere here, so you interpolate that position from which you get the form factor here. So, that is how the form factor is obtained in the from this test. So, you can see here this one k into Cf, that is what is marked. So, that depends on this curve. So, k into Cf represents the form factor. So, the reason, physical reason given for the form factor is that I think we have already discussed about that. Here the formula is based on the flat plate resistance. So, all this is then tests carried out using flat plates of different length and different width. In the flat plate, the flow velocity around the flat plate is different from the flow velocity around the ship. So, maybe better explained using a diagram. Suppose you consider a flat plate, consider as a flat plate. If you look from the top of the plan view, it may be this a plan view. It is now deeply submerged. So, you are just towing it at different speeds, then you measure what is the force required to tow it at different speeds. So, this length is usually taken as the ship length or model length, and this width is equal to half the average girth, mean girth. So, both sides put together gives a total. So, this represents the wetter surface area of the ship. So, now if you look to the from the top, this is a plan. Suppose it is moving in this way, this is moving. So, that actually the flow is in this direction. So, here the flow is like this, almost parallel flows you get. Okay. Now, you are representing this for a ship. Now, you consider a ship model or shape, just consider you just consider ship of almost same length, the same length. If the flow, if the ship is moving with, suppose this velocity is v, ship also moves with the velocity v, you see that because of the curvature the flow comes here, because of the curvature the ship velocity increases. The velocity here is going to be much more than this in free stream velocity. So, this increase in velocity increases the resistance of the ship, because you know that frictional resistance is proportional to V power 1.825. So, this velocity is the flow velocity. So, here in the case of the ship, due to its 3-dimensional form, the flow velocity is higher, which is not accounted here. So, this expression which has been developed, maybe the Schoner formula or Hughes formula or ITTC formula, where they use the flat plate resistance, they have not considered the increase in velocity of flow due to the form of the ship. So, that increases the frictional resistance of the ship. So, which is accounted by, that is why it is called the form, that is K is called the form factor. So, this K factor is basically due to the change in the flow velocity or increase in the flow velocity around the ship. So, that is a physical reason for such a difference. So, that is how. So, now you get the form factor. So, you use the same form factor for the ship also. So, this shows the extrapolated values of the resistance CTS for the ship, and ship operates at a higher Reynolds number. You can see that the total value from here to here, it is 1 plus K into Cf, and Cfs is coming from this expression. So, that is what is done in the Hughes method. So, in Hughes method, what he does is he uses the formula which I said before, the same formula. This is a Hughes formula for frictional resistance, and here what is it represents the total resistance as a basic frictional flat plate resistance plus the form resistance plus free surface, that is a wave making resistance. So, now he clubbed these two, both are having the viscosity effect. So, he just put 1 plus k into the base resistance flat plate resistance plus the free surface resistance. Now, he is suggesting how to find out k or 1 plus k. So, that is what is done here. From the model test what we discussed, you have the baseline and then use his formula baseline, then you generate curves with different multiplication factors 1.1 like. So, you get these curves over here. You have the model test resistance for different Froude number, you have like this, something like this it comes. The curve here is not exactly matching here, it will be something like this. So, that at low Froude number there is no wave making and the whole thing is due to viscous effect. So, the viscous effect you see that the resistance is more than the baseline. So, this more the additional resistance, this part is due to the 3-dimensional effect which I have explained of, due to the increase in velocity due to the form of the ship, that is why it is called the form factor. And once you get that form factor, the same form factor is taken for the ship also. So, with that you and then you are extrapolating it for the ship as we did before, as we suggested before, and then you get this curve and this total value what you call here it is 1 plus k into Cf the ship. So, that is here what I explained. Draw the baseline, draw 1 plus k curves for different values of, that is what I suggested now, that like you get 1.1, 1.2 factors. Draw the curve for the model for different speeds, that is what we have seen now. You have, this is a model for different, then the curve 1 plus k having tangent common with the curve is found to be the run point, and there by reading the 1 plus k. So, what you have is this curve goes like this, actually goes like this, and you find out that tangent which forms this, that is the 1 plus k. So, from which you read the 1 plus k and extrapolate that Cf into 1 plus k curve to shipped region, that is what you have done. Read Cw of the model at different Fn subtracting by subtracting this from the Ct. So, what you do is you here you have Cf plus Kcf, and from there you find out what is the difference, that gives a Cw. So, Cw you know it is same as Cw of model, same as Cw of ship. So, these two values are same, only difference here this Cf value changes. So, you put Cf using this formula Cfs, then you put the Cw here, Cw is constant, put the Cw here, then you get these points, that was, then you get this curve. So, that is based on the, so read of Cw of model at different Froude number by subtracting Cf into 1 plus k from Ct. Based on the Froude law, plot Cw over Cf into 1 plus k to get the Ct of ship, that is just I explained. Add model from to this, you add the model ship correlation elements, that is I said due to the change in roughness, due to the ship surface change, roughness of the ship and model are different. Ship model is very smooth, whereas for the ship it is not so smooth. The smoothness there are different reasons, that also we discussed before, due to painting, due to welding joints, or due to deformations of the plate, and there are many reasons for increase in roughness for the ship, and which is not present in the case of model. So, that increase in roughness need to be accounted when you estimate the total resistance of the ship compared to that of the model. So, that Ca, there is a correlation elements is added to that model value, and then you get Cts, and then you find out total resistance of the ship is equal to this Cts value into half rho Ss Vs square, that is the ship parameters, vector surface and velocity and density. So, you get total resistance of the ship from this, that is the Hughes prediction method. So, here that is the method which has been proposed by Hughes to estimate the form factor, and now we see another method called Prohaska's method, how to determine the form factor from the model test. So, this is a method proposed by Prohaska in 1966. So, what he has done is the 1 plus k factor, the form factor vary with respect, he has shown a curve. This is for each curve for a particular L by delta power 1/3, you can see that. So, delta power 1 for the same length, if you consider delta is small, delta power 1/3, is not it. This value will be, if delta is large, that is fuller form, then this value will be smaller. So, it is 4, 5, 6, 7, 8, that is the value. So, this side of the curve, that is when it is 4 means it is a fuller form shape, that is for the same length it has a more displacement, that the denominator is high, let us say the value is less. So, this region may be referring to a tanker ship or maybe a bulk carrier and all that. So, these type of vessels will have higher form value. So, you can see the 1 plus k and against the CB. So, you can see the CB value, CB is high, full form, and here you can see what is the form factor. If you consider this curve, the form factor is high, but when it comes to the smaller one, L by delta power 1/3 is small, that means 1/3 is high value 8. So, here that means the denominator is small, that is like container ship, the denominator is small, that is for the same length the displacement is less, it comes in this range. You can see that form factor is less, is 1 point less than 1.1, where here in this range it comes more than 1.2. So, that shows the indication how the body is more full, the higher will be the value of form factor. If the body is fine, because it is getting closer to the flat plate, the form factor is less. If it deviates more from the flat plate concept or assumption, then the form factor effect will be more. Prohaska proposes a method for determining a 3D form factor, that is what is that. He just put, you put k as a factor, Cv minus Cfo by Cfo, this is the factor he used. What is all these values? Cv is the total viscous resistance coefficient of the 3D form. So, the 3D form you consider, you find out the total viscous effect, viscous resistance, that is the Cv. Cfo is a frictional resistance coefficient of 2D flow, that is a plate flow. So, Cfo is coming from the formula and Cv is actually the measured one due to the 3D form. So, that difference divided by Cfo is given as k. So, where no separation, you do not consider separation here, only is the, here you consider only the form effect. Ct is equal to Cw, that is wave making resistance coefficient, plus 1 plus k into Cfo, that is wave making plus viscous effect. Viscous effect is Cfo plus this k into Cfo, k into Cfo is the difference. That means actually Cw plus Cv, you can see that k is equal to Cv minus Cfo divided by Cfo. So, that is, this gives that Cv is equal to k into Cfo plus Cfo, that is what is written here. So, this is same as Cv, which is coming from here. So, here I have said the Cw is a wave making resistance coefficient, and you already know that Cw is a function of that is Rw, you know already Rw is proportional to V power 6, we have derived in the previous classes. So, Cw is equal to Rw by half rho S V square. So, that means Cw is proportional to now V power 4, or we know that Froude number is equal to V by root GL. So, we can say that this is now proportional to Froude number raised to 4. So, Cw is proportional to Froude number raised to 4. So, that is how we have written like that. Cw is y is a constant into fruit number raised to 4. So, CW is proportional to fruit number raised to 4. So, Y is a coefficient and Fn is a fruit number. So, in the same thing is what I have explained, Rw is proportional to V power 6 and Cw is given by this relation, and from which finally you get this proportional V. So, what you have is if you look to the above relation here, Ct, Cw and all that, Cw is now is equal to Y into Fn raised to 4. So, from here you write Ct is equal to Cw into we have Ct is equal to Cw plus 1 plus k into Cf4, and we know Cw is coming from here. So, that is equal to Y into Fn raised to 4 plus 1 plus k into Cf4, or we can write Ct by Cf4 is equal to 1 plus k plus Y into Y or Fn raised to 4 by Cf4, isn't it? So, that is what you write. So, here that is what is shown. You can see that Ct by Cf4 is equal to 1 plus k, I think that is correct, plus Y, this is Y into Fn raised to 4 by Cf4. So, that is how you write that expression. So, what does it mean? This is, if you write, this is something like a equation of a straight line. Y is equal to mx plus c, this is y, c is this is referring to mx. That is, if you write if you plot a straight line with this as y and Fn raised to 4 by Cf4 as x, then you get a straight line. This is the equation of a straight line. So, that is what is done. You plot Ct by Cf4 divided against Fn raised to 4 by Cf, you get a straight line. The slope of this straight line is y and intersection is equal to 1 plus k. You can see that Ct by Cf4 is equal to 1 plus k into. So, here this is the vertical axis, same as y, and this is the x axis, which is x. So, it is y is equal to m x plus c. So, c is the intersection, which is 1 plus k. So, you have these red dots, the values coming from experiment at low Reynolds number, low fruit number. On these plots, for using this, what you do is you find out what is Ct. Ct is obtained, the total resistance from which you get Ct. Now, you find out Cfo from ITTC formula or any of the formula that is also known to you for that low fruit number. So, you can find out this quantity, and similarly you know what is the fruit number, and then the fruit number raised to 4, this also you can estimate from that model parameter. So, these two quantities are known. So, you plot this and this. So, now you get the experimental points, the red dots here. You connect or fit a straight line to these points, then this straight line intersect this axis, and that is equal to 1 plus k. So, you get this value here. So, here this intersection, that is how you get the form factor. This is a method suggested by Prohaska. So, you run the model at low fruit number and you get the resistance value, then you find out what is the Ct of the model, you find out what is Cfo from the ITTC formula or similar formula. So, you find out this ratio here. Now, you find out the model is run at a different fruit number. So, you know what is the fruit number divided by the corresponding Cfo again from ITTC. This ratio also is obtained from the model test. Now, you plot this ratio against this ratio. So, you get few points like this, and you know it is experiment, you do not get just a very smooth simple line. So, you just fit a straight line to that, because it, you know that is of almost following a straight line pattern, so linear variation, and this when you put it here or extrapolate to this, it intersects the axis, and this intersection it is represented by 1 by k. So, this value directly gives 1 by k, this is what is written here. So, here the model should be run at very low speed, generally Froude number between 0.1 and 0.22. So, that is what is done in the Prohaska's method. That is how the models, how you find out the form factor from the model test, and the same form factor holds good for the ship also. So, the uncertainty of measuring resistance at very low speed is relatively large. So, when you measure the resistance is very low at very small Froude number or very low speed. So, measurement also become difficult when it is a small quantity. This means that it is difficult to determine the run-in point, that is you have seen the Hughes method, what is the run-in point, that is the slope which comes in the bottom. So, the run-in point is, if you consider the total resistance, if you put a CT against Froude number, you get a value, a curve something like this. So, here and you have the CF value, CF coming maybe like this, because you know this is CF and we know it is proportional to V power minus 0.175. So, it goes like this, and the total resistance curve it just initially like this, because this region only is a frictional resistance, and then it goes like this wave making picks up in this region. So, this is called the run-in point. So, this is going to be right. So, this is accounting for the form factor. Okay. So, that is the point what it is called the run-in point. So, that is here what you see, it is a run-in point, that is a slope, that region. For fuller form, that is like container, bulk carrier or tanker shapes, the plot is concave curve. You can see that it is not, it is different, 1 plus k and or speed dependent. We see that what happens to the high power, you can see that it is not a straight line. If it is a full form ship, you can see that it is not a straight line, the points you see here, it is coming like a concave curve. So, it is curving like that, because for fuller form shapes the resistance we have seen is generally V power 6, but for fuller form shapes the resistance is not V power 6, it may be V power 7 or V power 8. So, when you use this relation, it is not going to be a straight line representation. So, what you have to do is you may have to change, increase Fn raised to 4 to Fn raised to 5 or Fn raised to 6, then you get a straight line, otherwise you get such a curve like this. So, what is that for fuller form, the plot is concave curve, that is what you see, 1 plus k and y are speed dependent. It may be better to use the power for Fn between 4 and 6. So, Fn we have used previously power 4. So, here it suggests that you use something more than 4, maybe 5 or even 6 instead of 4. So, that is how that is a Prohaska's resistance prediction method, or Prohaska's method for predicting form factor, not resistance, actually the form factor. Then we have seen now the resistance prediction method using Telfers, and also we have seen that it is practically not acceptable. Then we have seen the Hughes method, where he has considered the form factor also into effect, and next we considered a Prohaska's method to determine the form factor. So, these are the things what we have done, and now we have two prediction methods put forward by ITTC. ITTC initially put forward 1957 prediction method, and later it was replaced by ITTC 1978 method. So, the difference between 57 and 78 methods are in 78 method the form factor is also accounted for, whereas in 57 method the form factor is not considered. So, with this we conclude the today's class and to resume next day. Thank you.